Chapter 11 is about solutions. So this is going to be all about how things dissolve and why things dissolve and how we measure how much of them has dissolved. So let's start with how we measure it, and that is in units of molarity. So the first thing you need to recognize is that molarity and concentration need to go hand in hand in your brain. So molarity and concentration. Because most of the time in the question, they're not going to say, what is the molarity? Most of the time, they're going to say, what is the concentration? So you have to know that if they're asking you for concentration, they're asking you for the molarity. And molarity is always the same thing. First of all, its symbol is a capital M. So don't confuse this with a lowercase m or moles or meters. There's a lot of M's in chemistry, but a capital M is going to be molarity. It's the moles of the solute. And remember, the solute is the thing that gets dissolved. So it's basically how many particles of solute you have put into a certain liters of solution. And notice that it's not liters of solvent, it's liters of solution. So that means the solvent and the solute together. So it's always going to be in moles per liter. And you can do, as your unit, you can do moles per liter, or you can do capital M. So just make sure that you have your units correct before you calculate it. So for example, if they give you the grams of the solute, you just need to turn it into moles first. Same thing with the volume. If they give you milliliters, just make sure you put it into liters. The next thing is called mole fraction, and we've touched on this a few other times in AP Chemistry, but we haven't highlighted it a lot, and I think on the last quiz some of you will miss this. So let's just go over it again. It's kind of like a percent. It's like the percent of moles that you have, except you're not doing the 100. So you know how for a percent you do part over a whole times 100. This is just part over a whole. And that's it. There's no times 100. So for example, if you have this compound right here, XA, and I wanted to know the mole fraction of that, you can talk about the moles of just A, so N stands for moles, divided by the moles of the whole compound. So again, it's just a mole part over a mole total, and that's it. This next section, 11.2, talks about how and why things dissolve. So first, let's review the phrase like dissolves like. When I say like, I'm talking about polarity. So polar things tend to dissolve other polar things. Nonpolar tend to dissolve nonpolar, and it's difficult to get a polar and a nonpolar to dissolve in each other. We call them immiscible, which means they are not able to be dissolved. And then ionic compounds are kind of like extreme polarity, and so they can dissolve too based on the solubility rules. So you would use the solubility rules for ionic compounds. So if you're given a substance and it's the question is, will this dissolve in water, or will this dissolve in nonpolar oil or something like that, what you normally need to do is to determine whether or not it's polar or nonpolar, and you probably need to draw the Lewis dot diagram because you want to see if you have extra lone pairs on the central atom. That would affect the polarity. And then you also figure out the polarity of the solvent and then see if they're the same or not. And then again, if it's ionic, you don't have to draw the picture, you just can use the solubility rules to determine if it dissolves in water. Step B is kind of an important topic when we're talking about, like, if there's an essay question about how something dissolves. So there are several steps that have to happen in order for it to dissolve. So first of all, dissolving is complicated because it looks like something disappears. So a lot of times students think it's a chemical reaction or, something's happening there. It's not a chemical reaction, it's a physical change. And basically you're just breaking the substance into such small pieces that you can't see it. So there's a couple of things that have to happen. You have to break up the solute into individual components. So if you have a crystal of sodium chloride, NaCl, you've got your sodium and your chlorine. It's a 1-to-1 ratio. So you have to break off a sodium ion and break off a chlorine ion. Then you break off a sodium ion, break off a chlorine ion. So you have to break off these individual ions. And anytime you break a bond or separate intermolecular forces, that requires energy. So notice that that part of the process is going to be endothermic. You also have to overcome the intermolecular forces within the solvent to make room for the solute. So it's kind of like you have to spread out the solvent to allow those new particles to kind of get dispersed within the solvent. So again, you're breaking a bond. You're not actually breaking a bond. It's an intermolecular force, but it's like you're separating things, and that requires energy. So that process is endothermic. And then what happens is that the solvent can surround the thing that it's attracted to. So in this case, if we're doing water, the hydrogen part of water is slightly positive. So when water surrounds chlorine, it's important that you understand that hydrogen is the atom that's going to touch the chlorine ion, because hydrogen is slightly positive and chlorine slightly negative. The opposite will happen with sodium. So for sodium, water will flip itself so that the oxygen is near the sodium ion, because oxygen is slightly negative in the water molecule. So it's important that you can explain how the water surrounds those particles, and just make sure you're keeping in mind that opposites are attracting. And the attraction is going to be exothermic, because anytime you form a bond or form an attraction, that's going to release energy, because the only reason they would form an attraction is to become more stable, which means they're at a lower energy, and so they have to release the energy that they don't need anymore. There's a couple of things down here. You can talk about the enthalpy, or the heat of the solution, which is delta H. And the delta H of the solution is going to be all three of these steps together. So it might take a whole lot of energy to break up the solute, and then you don't get much energy when it actually dissolves. And so overall, the process could be endothermic. Or you could take very little energy to break apart the solute, and then you get a whole lot of energy when the solute is dissolved and it's attracted to the solvent. So it just depends on which of these processes is more significant, what the overall delta H of the solution will be. You can talk about factors that favor the solution process. So negative value means that it's more exothermic than when it started. We can talk about it in terms of entropy, which is the chaos. We've talked about that word before. So as you increase the chaos of the solute, as they break apart into pieces, you have more entropy, which is favored in nature. So what we're looking at to determine if something dissolves is all of these factors. How much does it increase the entropy? How much is the endothermic part of the solution process? How much is the exothermic part of the solution process? So we look at all of those and try to figure out what is the most significant, and that determines whether the overall process is a positive or a negative value in terms of delta H. And then the last thing for this section is electrolytes. And we've talked about these before, but they're really important because we use electrolytes a lot. You use them in your body. We use them in all kinds of reactions. And these are valuable because they produce a strong electric current. So there are two reasons why an electric current could be produced. Either if you have flowing electrons, so for example in metals, that sea of electrons that happens in metals is just those free-floating electrons. That's what allows metals to be good conductors. But you can also have free-floating ions. So if you put these ions of sodium chloride into water and allow them to separate into charged particles, because you have floating charged particles, you can conduct electricity. So anything that breaks apart easily into charged particles is going to be a strong electrolyte. So the strong acids, there are 6 of them, so make sure you're familiar with them, or at least know where to look them up for remote learning. There are only 6 of them. Make sure you can talk about the fact that they're strong electrolytes because they break up completely or almost completely. It's so close to 100% that we usually just round up and assume 100%. And same thing with strong bases. Strong bases are going to be things in group 1 and 2 with hydroxide. So like sodium hydroxide, potassium hydroxide, calcium hydroxide, we consider those to be strong bases. Anything in the first 2 columns bonded to hydroxide. And again, what makes them strong is that they actually break apart almost completely. And so for every NaOH that you have, you're going to end up with a sodium ion and a hydroxide ion. So you get a whole lot of ions out of it, which is why they produce electricity well, or they produce currents well. They can have an electric current, is what I should say. They're not actually producing the electricity. So all 3 of these, strong acids, strong bases, and then ionic salts are anything that when you look up on the solubility rules, if it says that they dissolve in water, they're going to produce a lot of ions as well. So all 3 of these, because they produce a lot of ions, they break apart almost completely. We consider them to be good electrolytes. Weak electrolytes are ones that will produce some ions, but not enough to make it a strong electric current. So they'll produce, like if you hook up a light bulb to a solution that has a weak acid, you'll get a very dim light on the light bulb, whereas with a strong electrolyte, you'll get a bright light. So the amount of ions that are flowing, they have to be charged particles and they have to flow, but the amount of ions that are flowing are going to determine whether they're good electrolytes or bad. And weak electrolytes do not break up well. In fact, we usually keep them together when we write ionic equations. So for example, if we were writing, hydrofluoric acid, when it dissolves, it makes H plus and fluorine ions, and the fact that it makes H plus is what makes it an acid. But I think it's less than 1% of this will actually break up. So like over 99% of it is going to stay together as HF, and very few particles will actually break up. It's enough particles to consider it to be a weak electrolyte, but it's just not very many compared to the strong electrolytes. And then non-electrolytes are things that can dissolve, but they don't produce charged particles. So sugar is a covalent compound, and when it dissolves, it breaks into individual sugar molecules that are neutral. And so you don't get those charges which are required for that in order to conduct the electricity. And alcohols are another one, and then most of the covalent compounds for the same reason. They won't break into charged particles, they just break into neutral compounds, and so therefore you can't conduct electricity. So again, if you're ever asked about an essay question about producing electric current, there are two requirements to have that electric current go through the solution. You have to have charged particles, and they have to be able to flow. So table salt by itself is not an electrolyte. You have to put it into a liquid where it will dissolve, and those ions can actually flow around each other. So you have to have ions, and they have to be able to flow. And that's it for today.